Alright, page 2b is mostly a recap of slope, distance, and midpoint formulas. If you don't know, slope is given by the change in y. The change in y, y2 minus y1 over the change in x, x2 minus x1. Slope is a measure of rate of change. The distance, which we discussed, was a rework of Pythagoras' theorem. x1 minus x2 all squared plus y1 minus y2 all squared. And of course, the midpoint, which is m equals, the midpoint is given by, you would say, let's say, x1 plus y1 over 2, comma, x1 plus x2, and then y1 plus y2 over 2. Sorry, hopefully that pencil will cooperate with me. It's being kind of rude today. So here we have a kind of a challenge problem to work on. If you're going to try this on your own, read the directions and then go through, rate these as either true or false. Rate these as true or false and then say why. And then here try and add this, try and actually make this addition to the problem. Make the addition here. So that's the goal for you guys. Pause now, try this on your own. Shouldn't take you too long. Just quickly working through. Anyway, so for the description it says, below is the Shirley Fine Arts Museum floor plan. Each square corresponds to 15 feet. So that means like here to here on one of these squares, that's 15 feet, right? It says the edge of the graph encloses the permitted area as there are streets on each side. So, and then also the border of this graph here is the very edge. This is the outside. So past here is like impermissible. You can't be, like for example, if you were to build a wall that goes out here, that would not be a permittable wall because it would go into the street. So anyways, the design intention was supposed to look like this. Segments AB and FB are perpendicular to AG. So first, I was going to prove this true or false. Let's look at segment AB. Here's AB right here. All right, then let's look at segment FB. AB and FB are perpendicular to AG. It's supposed to say FG. So sorry guys, this is supposed to say FG here. They're perpendicular to AG, and AG is shown here. Now these may look pretty close to perpendicular, especially these. This looks pretty close to perpendicular, but it's not quite perpendicular. The way you can test is by remembering, maybe in the margin over here somewhere, maybe you might write, if slopes are perpendicular to one another, then they're the opposite reciprocal of each other. So remember, you have to flip that fraction and negate it. Flip it and negate it in order to get a perpendicular, oh, my iPad's freaking out. Perpendicular, what in the world? Sorry guys, my iPad's losing its mind. To get a perpendicular slope. So for these I'm going to count. Let's see, in blue I'll do the y direction. So this will be, I guess let's stay consistent with the last page. Blue can be the x direction actually. So in the x direction, there's 2. In the y direction, there is 4. So I'm going up to the right. That's a positive slope. It looks like 4 over 2, which is 2. So this is a slope of 2. All right, and then over here, same thing. If I'm trying to see if it's perpendicular to this line, I'm just trying that stuff out. Whoa, what? I'm just trying stuff out. So I'm going to try this x direction. That looks like 1, 2. 1, 2, 3, 4, 5 across. So that's 5. And then in red, we have another 2. So this one looks like negative 2/5. So one slope is negative 2/5, the other's 2. Are these guys perfect opposite reciprocals? No. The opposite reciprocal of 2 is negative 1/2. So if this were, if this were 2.5 over 2 over 5, then it would be, so they're kind of close, right? They're kind of close, but not really. They're not actually perpendicular. So you'd say, no, this one's false. Since, and you might say something like, the slopes, like slope 1 is not equal to the negative reciprocal of slope 2. That would be just a brief reason why. For segment FE to be perpendicular, sorry, I'm kind of sick, so we're going to try this next one. Segment FE is perpendicular to segment GF, so let's go here. Let's see FE. There's FE, and here is GF. This is what we just looked at. So we already know that GF has a slope of 2. If we look at this one, it looks like it's going down 1, so the top is 1, and then the bottom is over 3. So the slope of this guy is over 3. Remember that the slope, I'm knowing this just because it's the change in y over the change in x. Right? Slope is y over x. This one's 1/3. They're not quite, and it is a negative slope, so we probably should keep that in there too, right? We know it's negative because as we move in the positive x direction, our slope goes down, which is negative in the y direction, so it's a negative 1/3. And so while they are close, no, they're not quite perpendicular, so same thing for this guy. This is also false. And I'm just going to write same over here, all right? Then it says the length of no walls exceed 100 feet. So if I know each square is 15 feet, I can check the length of these by looking at each square. So if like here would be 15, there would be another 15, would be 30, right? And I could keep going, count all the way up. If I did all the way across, this is 1, 2, 3, 4, 5, 6 ways across. 6 times 15 is 90. So this one is 90 feet. So this wall is good. It's under 90 feet. So you could check off. Now you only need to find one wall that's greater than 90 feet to make this false. Right? There only needs to be one wall that we're actually looking at. Oh, I'm sorry. iPad is killing me. Okay, thank you. It like won't slide every time. I don't know. It won't like slide around when I want it to. So the goal here, we want to say no walls. If any walls exceeded 100 feet, this would be false, right? So if we just have to find one wall that's too problematic, well, A to B looks pretty long. Let's check that one. If the other ones, if this one's not 100 feet or more, then the other ones definitely aren't. So we'll check this one. Let's see. Now, how many squares is it from here to here? We really can't tell, right? Like it looks like. I mean, it's let's see, it's 3 this way. Sorry, 4. I meant 4 this way. If I redraw it over here, it looks like this, right? There's 4 this way. And there's 1, 2, 3, 4, 5, 6 this way. Right? So how long is this line? Well, this looks like a Pythagorean theorem problem. You could use a Pythagorean theorem, or, if you recall from earlier, the distance formula is just the Pythagorean theorem, but rephrased for our purposes. So let's just do that. So here's the distance. The distance formula looks like this is the distance in the x direction. And here's the distance in the y direction, just like we've been doing on the last page for fractional distance, right? If you subtract those numbers, that's how far they are apart. So what I'm going to plug in here is that this is actually 6. It's the distance, not x1 or x2, but the distance itself. And same thing for the x direction. So if it would let me scroll down, that'd be great. Down here for this problem, okay, please. I don't know what's going on, guys. Please. Okay, thank you. I don't know why it won't. So here for the distance formula, it would be d equals the square root of. Now, I know it is, let's see, it's one side is 6, the other side is 4. So the change in the x direction is 4. And that would be squared. Notice I'm plugging in the entire change and not just one direction. Here's 5. This would be 6 squared, all right? And now this would be equal to 16 squared. I'm sorry, excuse me. 4 squared is 16 plus 6 squared is 36, which is the square root of 52. 52, I guess. Now the problem with this is how many squares there are. There's the square root of 52. Golly, the scrolling. There's a square root of 52 squares from here to here on this line, whatever number that is. So in our calculator, and I'm just doing this in my phone calculator, but you can do this anywhere. Desmos or something like that. Let's see. We have 52, and I'm just going to take the square root of that number, and it comes out to 7.2. Oh, I'm writing in the wrong thing. Oops. About 7.21. All right, so just about. It's not often, pretty typical. If you use a distance formula, you're going to get a wacky number at the end. So it's okay to get a decimal here. It's just an approximation of a square root, so it's very likely to get it. And then same thing. Now that we know it's 7.21 like tiles across from A to B, well, how many feet is that? We need to multiply each square. Golly. We need to multiply the distance across here that we just found by 15 feet, because there's 15 feet in each square. So 7.21 times 15. And now in my calculator, I'm just going to go back and try that. It says about 108.16 feet. Well, since that's greater than 100, you would say this is also false. So actually, all three of these are false. This is not a very well-made museum by Mr. Shirley. All right, if you guys wanted to add these walls, it would not be too bad. You would just come over here. We want to make sure that they join at E and D. So up here, I'll erase the stuff that's in the way. I want to join at E and D. So here's my 2 points I'm tacking the walls onto. Then it says these walls should be longer than segment GF. So let's see, where's GF? Well, GF is longer than, let's see, it's about, about more than 4, right? You would say greater than 4. Okay, that's fine for now. And then it says these walls are parallel to segment AB. So let's find AB. It's over here. We saw that segment AB has a slope of, let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So it has a slope of 3/2, which you can see here as well. So I'm going to slope of 3/2 on these lines. So I'm going to go 3 and then 2. And then I would have to go a little bit more to make it longer than GF. So let's go like, I don't know, how long is GF? Like about that long. So let's go about that length, just measuring with my hand. Oops. Out to like, I don't know, right there. That has about the same slope. And you can see that the problem is that it goes off the chart. So it would actually be that these can't be added. You wouldn't be able to add these walls because it would come off. And then same thing here, we make them parallel by doing a slope of 3/2 and then continuing down to about the same length. It could go all the way down to here, it could come up to here, it could be either way. These would be the walls we tack on. Doesn't look that great. So your finished picture looks kind of hectic, but that's okay. All right. Really, the goal here is using distance formula, seeing parallel and perpendicular, which will be practiced more on the next page. If you're worried about this page, I would say don't fret over 2B. Try 2C on the next page instead. That'd be probably a better representation. See you guys on that one.